Hi, I'm Fernando Pereira from UFMG, and today we will talk about conventional SSA form. We have, in the last class, discussed an algorithm that finds control dependencies in a program through a traversal of the program's dominance tree. However, there is one point that serves special attention. That algorithm works well for programs in a format that we call conventional static single assignment form. And today we talk about this format. To explain what it is, let me introduce a new notion, phi-related variables. Two variables are phi-related if they appear in the same phi function, either as arguments or if one of them is a definition. Additionally, two variables v1 and v2 are related if there is a variable v that's related to both. So this notion is transitive. And we say that a program is in conventional SSA form if no phi-related variables have overlapping live range. Usually this is true right after we convert a program to SSA form. Would you like to think about why this is the case? However, there are optimizations like constant propagation, for instance, that might break the conventional property. Let me give an example. The program on the left is in conventional SSA form. There are three phi-related variables, v, v0, and v1, and their live ranges do not overlap. Now imagine that we do copy propagation. Then we replace v1 with x. Now v0 and x are phi-related, and they are both alive at label L2, for instance. They are phi-related because they appear in the same phi function. In this case, the program is no longer in CSSA form. Many algorithms that work well in SSA form stop working correctly if the representation is non-conventional. The algorithm that we had is one of them. For instance, consider the program on the right. What is the slice for the criterion L4, this instruction here? The predicate v0 used in the branch at L2 does not control any variable because there is no variable defined within its influence region. But clearly this predicate determines how the phi assignment happens. So the phi function is controlled by v0, but our algorithm wouldn't find it. However, it's relatively simple to deal with programs in non-conventional SSA form. We can convert them to CSSA form, or we can use an adapted version of our algorithm. Let's explore the two alternatives. First, converting a program to CSSA form is trivial. Just split the live range of all the incoming arguments of phi functions right on the incoming edge. Notice that we need to eliminate critical edges for this to work. So on the right, we have the optimized program, now back into CSSA form. Notice that this transformation sort of brought back the benefits of the optimization that we had seen before on copy propagation. In the end, we might have more copies in the program. Another option is to extend the algorithm to add edges from predicates to phi functions. We need to add an edge from the predicate to the variable defined by a phi function at the post-dominator of the predicate. Note, when I say post-dominator of the predicate, of course, I refer to the post-dominator of the block where the predicate is used in a branch. So L4, the block that contains L4, is the post-dominator of V0, meaning that this block is the post-dominator of the basic block that contains this branch in which V0 is used as a predicate. Notice that we only need to add these edges if the arguments of the phi function are different. If they are the same, then regardless of the predicate, the phi function will be performing the same copy. Like in this example, independent of the value of v0, the phi function will copy x into v. And with this discussion about conventional SSA form, we close this class on program slicing. Most of the concepts approached in this class were taken from the classic paper from Gian Ferrante from 1987, this paper that was published in Toplas. The algorithm that we saw was taken from this paper by Rodriguez et al., published in 2016 in Compiler Construction. Thank you.